May June 2024, Paper 4, Variant 2. Question 1. A. Describe the trend in the solubility of sulfate of the magnesium, calcium, and strontium. Explain your answer. Okay, so first you need to give the correct trend. Okay, so we know that when it's down the group to sulfate, the solubility decreases. So the most soluble sulfate is magnesium sulfate, followed by calcium sulfate and strontium sulfate. So there are a few points that you need to use to answer this solubility. First, you need to recall or use the equations here. The enthalpies of solutions equal to the enthalpies of the hydration minus the lattice energy. So later we use this one for the comparison. So for this, after the trend, so the first thing that you need to mention is these two enthalpy. Okay, the lattice energies and the hydration enthalpy both become less exothermic, means both decreases. It's most likely because of the size of the cations is getting larger. So the attractions between the ions is getting weaker. So therefore, it becomes less exothermic, means it's released less heat because of the size of the group 2 cation is getting larger down the group. So what you need to say is both enthalpies now become less exo, or you can say that both decreases. Decreases is in the magnitude. So second you need to mention is if both decreases, which one decrease more or which one change more? So in this group 2 sulfate solubility, the one that decrease more or changes more is the hydration enthalpy. So this one is change or decrease more than the lattice energy. It because the lattice energy is not really affected much by the change in the size of the cation. Because the sulfate itself is too large, 1 sulfur 4 oxygen. That's why the size of the cation, it will not really affect the lattice energy that much. That's the reason why the lattice energy decrease lesser, and the hydration enthalpy now it decrease more. Okay, when the hydration enthalpy decrease more, means this value will be more positive. So means this value when is minus the lattice enthalpy, the enthalpy change of solution, it will be more endothermic. More endothermic means it's less soluble. Whenever the enthalpy change of solution is more endothermic, means the salt is less soluble. Okay, that's the relations that you must know. Which one it decrease more, which one is cause the dye solutions more endothermic now. Right. So these are the few points that you must understand and know how to use. Okay, I hope you understand. If you are not really clear or the explanation is not enough, you might check or you might refer back my previous video. For my previous video, I explained a lot about this solubility of these sulfates and hydroxide. Okay, you can check the previous video. Part B, define lattice energy. Okay, this one is very easy. Energy change when 1 mole of ionic solid is formed. Okay, the 1 mole of ionic solid is important because lattice energy is always 1 mole of this compound or ionic solid is formed, and this solid need to form from its gaseous ion. This is another keyword. It must from the gaseous ion under standard condition. The standard condition normally is 1 atm 298 Kelvin. part C. State and explain the main factors that affects the magnitude of lattice energy. As I told you just now, lattice energy is from the gaseous ion. Means once the gaseous ions they form bonding and release energy. So these bondings that form and the energy that release, it depends on two factors. It depends on how large is the ions and how many charge inside that. Okay, I use two examples to explain. Let's say now we have sodium chloride and magnesium oxide. So we know that sodium ion is larger than magnesium ion. They are neighbors. This is group 1, this is group 2. So the ionic size of the sodium is larger than this magnesium. And the magnesium has more charge. So we know that the magnesium ion has a greater charge density. And for this chloride, so chloride is also larger than this oxide, and the oxide has more charge. It has 2 negative. So if we compare these two compound ionic solid, so we know that the attractions between the magnesium oxide is much stronger than the sodium chloride. It's just because of these two factors: the ionic radius or ionic radii, and the charge. How many charge inside there? Eventually, it will contribute to the things we call charge density. So we know that magnesium oxide now has a greater charge density, and these two ions they can form a stronger bonding and release more energy. That's what you need to understand and answer, right? If you know, then this is 2 points that you must explain. Okay, as ionic radii increases, okay, the lattice energy become less exothermic. Means if let's say now the atomic radii increases or more, so for example like sodium ions and this chloride, so when it's increased, then lattice energy become less release less energy because the bonds that form is weaker. And another one, if let's say the ionic charge increases, the lattice energy become more exo. More charge means stronger attractions, stronger bonding form, and release more energy. So it's more exo. Okay, part D. For table 1.1, we need to use some of these the enthalpies to calculate the lattice energy. So this one you can actually refer to the question paper, right, if you want. Okay, part 1. There is a Born-Haber cycle need to complete, and is about the potassium sulfate, the K2S solid. Include the state symbol for all the species. Means you need to complete all the species, and of course the state symbol is very important because you need to show that it's a gas or it's a solid, right? Okay, so let's start from this part. From the potassium and this sulfur solid, and these two they react and form the solid. This one is obviously the formations of the potassium sulfate, okay, because it's from 1 mole. And after that, let's move up. So let's make it this one, the first one, as the atomizations of the potassium. So from this potassium solid to form the gaseous atom, so it's 2 times of the atomization of potassium because it's 2 moles here. And after that, this potassium solid now form the potassium gaseous atom. And the next step is just make it ionization, because after it's from gaseous atom, so it will ionize. So is next step will be the first ionization energies of potassium. So also 2 times, okay, because 2 mole. And after that, it will form the potassium's gaseous ion, and of course release 2 electrons. Okay, so next step, let's make it to the atomization of sulfur. From the sulfur solid, now form the gaseous atom. So this is the the atomization, and it's just 1 mole. And after that, when it's formed this gaseous ion, this gaseous atom, then this gaseous atom will gain electron. In this Born-Haber cycle, it has 2 steps here. Means it's telling us the electrons is going to add 1 by 1. So the first one is the EA1, the electron affinity of this, the first electron affinity of the sulfur. So it's going down, so it's exo, and the sulfur gaseous atom now form the sulfite gaseous atom with 1 negative charge, and this sulfur gaseous sulfite gaseous ion, it will gains another electrons and form the sulfur 2 negative gaseous ion, and these 2 gaseous ion now they will combine and form the solid. So these 2 gaseous ion combine to form the solid, and the enthalpies that involved is the lattice energy there. Okay, so this is a complete Born-Haber cycle from all the infos that given. And after that, calculate the lattice energies for the potassium sulfate. Use data from table 1.1. So I will not get back to the table. You can get all the values from the question. So I will just use this Born-Haber cycle in order to get this. Okay, let me make it a bit smaller so you can see the whole diagram. Okay, so for this one, in order to calculate the lattice energy, so we need to start with this formation. So we know that when we add this one, this, and this enthalpy, when we sum up all this enthalpy, so it's going to equal to the formations of this potassium sulfate, right? So therefore we have this relation. Okay, this relation. So we have this one. So the formations of this potassium sulfate, so is equal to all these enthalpies. So make sure you multiply with the correct factor, right, for this atomization, i.e. Atomization of sulfur, EA1, EA2, and lattice energy. Okay, so substitute all the values that given by the table 1.1. So you get all these values, right? Okay, substitute to this equation. So the lattice energy you get negative 2116 kilojoule per mole. Okay, so I hope you understand, and thank you.